Hello, my name is Bartosz Bednarczyk. I'm a PhD student at the University of Wrocław and TU Dresden, and this is a pre-recorded talk for FSTTS 2021 titled On Classical Decidable Logics Extended with Percentage Quantifiers and Arithmetic. This is a joint work with Tony Tan from Taiwan, and this talk is also based on the bachelor thesis of Ania Pacanowska and Maja Orłowska, written under my supervision at the University of Wrocław. To motivate our research, we consider an election knowledge base in which we have two parts. We have a database part and we have a knowledge part. So in the database, for example, we have the following fact that I'm a citizen of a given city and that I voted for a person called XYZ. An additional knowledge in this case is that every citizen voted for someone. We would like to formalize a concept of a winner of the election, and this can be done in the DL-like language as follows: that the winner is precisely the person that is a citizen and has more than 50% of total votes. So more than 50% of predecessors of voted for relations. And observe that in this setting we must have two properties of our logic. Namely, we need to have inverses of relations because we would like to count over them, and we would like to have percentage quantifiers or some form of percentage counting to impose a certain restrictions on the following concepts. And unfortunately, there is no decidable logic that is available at the moment, so we would like to fill this gap and propose a decidable logic that can express this kind of concepts. Related work is as follows. So there is a logic called Pressburger modal logic by Stefan Demry and Denis Lugier. But unfortunately, this logic cannot express inverses of relations. Similarly, there is an ALC with expressive cardinality constraints by Franz Bader, and it has the same issue. And in more general setting, we have a family of algebraic modal logics, but again, they cannot express inverses of relations. And all of this logic can, of course, capture percentage counting. And then we have two logics that can express inverses and percentages. So for example, there is a logic called ALCI SCC++, whatever it means. And this is done by Franz Bader and the other people in 2020 in ICAI. And there is also a logic called FO2 with Hartig quantifier. But unfortunately, both of these logics are undecidable. So we cannot really use them for reasoning about winners of elections. So in this talk, we will focus on two classical decidable fragments of first-order logic. And FO2 is the fragment of FO in which I can use only two variables, call them x and y. And this logic is known to have a finite model property. So every satisfiable formula has a finite model, and the overall satisfiability problem for this logic is known to be complete for non-deterministic exponential time. And the logic is not that trivial as we can reuse variables. So, for example, this formula specifies that every element has an outgoing path of length at least 3. So I can reuse x, then quantify over y, then reuse x again, and so on and so on. And this logic is expressive enough to capture many description logics like, for example, ALC and also modal logics. Another fragment that we will consider is the guarded fragment, and this is obtained by restricting FO in the following sense that we relativize all the quantifiers by atoms. So whenever I would like to quantify over a tuple of elements, I must first guard it by some atom. Right? So all the quantification must follow this pattern. So whenever I quantify over y, I must first guard all the three variables from phi, and whenever I quantify with universal quantifier, here I must also guard all the three variables from phi. And this logic is also known to have the finite model property, and the satisfiability problem is known to be doubly exponential time complete. And this is the example. We would like to formalize that some artist admires only beekeepers, and it can be done as follows. And here I introduce x, so I must guard it. And then I have a formula with a free variable y, and I also must guard the variable y. So for example, this formula admires xy guards the variable y. On the other hand, the co-example is as follows. Every artist admires every beekeeper. And here we have a variable x, and this is of course guarded by the atom artist of x, but then we introduce y, and we have a formula admires xy, so we must guard both x and y. But here we have only a guard for y, so we can't have a guard for x. So this is not a correct guarded fragment formula. Okay, so as I told you, FO2 can capture like classical description logic like ALC, and also the same holds for the guarded fragment. And they also can specify inverses of relations, but this is a very easy exercise to show that this logic cannot express percentages because they are fragments of first order logic, for example. So we would like to add like percentage constructions to these logics, so the resulting satisfiability problem will be decidable, and we can formalize this motivating example from the previous slide. And we will add percentage quantifiers in two different semantics. So we have a global semantics in which we have global percentage quantifiers. So whenever I will write there exists k% x's such that phi holds, I count all the elements from my domain, I select these satisfying phi, and there must be exactly k% these elements among all the elements in my domain. If you would like to see the formal semantic, it's here, and so we can pause the video and check it. Then we have a local semantics of percentage quantifiers in which the quantifiers are relativized by atoms. So whenever I will write a quantifier, there exists exactly k% r x's such that phi, I count all the successors of R relation, and exactly k% of the successors should satisfy phi. And again, the formal semantics is here, so we can stop the video and check it. And notice that the global and respectively local quantifiers make sense only if we have a finite domain or we have a finite branching structures, because it doesn't make sense to have, let's say, 30% of infinite elements, because it will be infinite. So over infinite domains, everything trivializes, so it doesn't make sense to consider percentage counting. So that's why we would like to consider either finite structures or infinite but finite branching structures in the obvious sense. Our results are as follows. So first of all, we'll show that unfortunately the finite satisfiability problem for FO2 with percentage quantifiers is undecidable, and it will hold over two semantics, either global or local. Then the satisfiability problem, the finite satisfiability problem for the guarded fragments is undecidable also under two different semantics. Then we would like to meet in the middle and consider an intersection of this logic, so an intersection of FO2 and the guarded fragment, which is the two-variable guarded fragment, and this logic is still expressive enough to capture standard description logics like ALC. And for this logic, we will see that under the global semantics of percentage quantifiers, the logic is still undecidable, but if we will focus on local counting, then the picture is quite different. So for finite branching structures that can be possibly infinite, we have an exponential time algorithm solving the satisfiability problem over such structures. And also we have a problem of conjunctive query entailment, which is quite popular in description logic setting, and we can show that this problem is doubly exponential time complete. So we have a doubly exponential time upper bound, because the lower bounds holds already for ALCI. If we have finite structures, but not only finite branching, but really finite, then the picture is again different, and everything is a way more difficult. So for the finite satisfiability, we can show that the problem is in triply non-deterministic exponential time, so quite high. And I believe that this can be improved to a single exponential, but it's very tricky. So already, if you will think about the guarded fragment plus counting quantifiers, so the membership of the satisfiability problem over finite structures to exponential time, it's quite difficult. And this is a work by Ian Pratt-Hartman. So in the remaining time, I will try to give you some ideas how the proof goes. So we will just go through all these results. I will tell you how the basic ideas look like, and then I will tell you in more details how the undecidability proof for FO2 plus percentage quantifiers goes. Okay, and in addition, our positive results hold also for Pressburger arithmetic formulae, so we can write even more expressive constraints on the successors that are written in the FO theory of natural numbers with additions. Okay, so the overview of our proofs is as follows. So first of all, to show undecidability of FO2 plus percentage counting and GF2 with global percentage counting, we first of all, we can observe that one can axiomatize universal roles with for all x, for all y, R of xy. So then everything gets guarded immediately. And then we can put these dummy guards everywhere and the semantic doesn't matter. Moreover, whenever I will add an R relation everywhere, it doesn't make sense it doesn't make any difference whether I will use local or global semantics, because it will be just the same. And the main idea is to follow like general undecidability scheme from the work by Franz Bader and the others to reduce the satisfiability problem to the Hilbert's 10th problem of solving equations over natural numbers. And that's it, and this proof will be explained in more details soon. Then, to show undecidability of GF with local percentage counting, we first check that FO3 with functional roles is undecidable, and then we will see how to enforce that the given role is functional. So that's how we can get undecidability. And for the remaining results over finite branching but possibly infinite structures, we can prove exponential time membership of GF2 with local counting. And the main reason why we can do that is that whenever there is a model for our formula, there is also a model that looks like an infinite tree, and this tree is of exponential branching. So we can get this exponential branching from some theorems on linear equations. So we can just guess this model on the fly. So I guess the element, which is the root element, then I guess the successors, and then I alternatingly choose one of the successors and go down and go down and go down like a Tableau algorithm, and I can stop after exponentially many steps because I will see a repetition of some type. So that's the rough idea how X-time membership goes. And for the finite satisfiability, we cannot really use the same trick because we really exploit the infiniteness of our structure. But for the finite structure, we need to loop back at some point. We cannot always take a fresh witnesses for some existential requirements. We need to have a finite model that must be looped somehow to get a finite structure. So that's why we would like to translate our logic into C2, which is the extension of the two-variable logic with counting quantifiers. So I can express that at least k elements satisfies phi, or exactly k elements satisfy phi. And it is known to be a complete for non-deterministic exponential time complete. And then we first simplify a bit our formula. We get rid of nested quantifiers, so we basically reduce nesting up to 2. And then we express local constraints that we have on the elements in terms of Pressburger formula over types. So we have a suitable notion of type, then we describe everything with a Pressburger formula, and we use a famous theorem stating that like a vector satisfying Pressburger formulae are exactly semilinear sets, and we can describe semilinear sets in C2. So we get a huge blow up. We take this local neighborhoods expressed in Pressburger arithmetic, we translate everything into semilinear sets with a huge blow up, and then we describe these sets in the two-variable logic with counting. And that's how roughly our reduction works. Okay, and for query entailment, we just reuse the existing techniques based on some pumping arguments. So we would like to obtain models of a high graph so that from the query point of view, our finite models and infinite ones will look the same, infinite tree-like ones, from the perspective of a query. Okay, and now I would like to give you like intuition why FO2 with global percentage quantifiers is undecidable, and I will present you two tricks. So the first trick is as follows. So let me call a structure A half RJ separated, and here is the picture on the right hand side. If first of all the symbol half labels exactly half of the domain elements, that's why it's called half, and R and J are in different halves of a model. So as you can see in the picture. And over such structures, I would be able to express equicardinality statement. So I would be able to express that the number of elements satisfying R will be exactly the number of elements satisfying J, under the assumption that half labels exactly half elements, that R and J are disjoint and are in the different halves. So how we can do that? And we can do that as follows. So first of all, I specify that exactly 50% of elements satisfy half and not R. And then, so I basically take half of the elements, I throw out the elements not satisfying R, and then I give back the elements satisfying J. And if it sums up into 50% precisely, then it means that there must be the same number of elements satisfying R and the same number of elements satisfying J. Otherwise, we'll not get precisely 50%. Okay, so it's just the method of throwing things away and putting our things back. Similarly, we can express functionality so that a given relation f from R to J is functional. This is depicted as follows, and we can do that like this. So whenever we have an element that has an f successor, I take precisely 50% of elements satisfying half, and then I throw the current element and I put back all the elements that are f successors of x. And since there is precisely one element here, I put back precisely one element from f, so f must be functional. Okay, so these were two main tricks in our undecidability proof and how the undecidability proof goes. So first of all, we have a notion of a simplified Hilbert-Stanf problem, SHTP in abbreviation. So an instance of this problem is just a system of equations, and every equation looks as follows. So either I have a variable and I say that this variable is equal to 1, or I have a sum of two variables, or I have a product of two variables. And in SHTP, we ask whether an input system of equations, epsilon, has a solution over natural numbers. And this is well known that this problem is undecidable. And in our reduction for a given system of equations like this, we would like to find a formula phi which is written in FO2 with global percentage counting, such that our formula is finitely satisfiable if and only if our solution, if our system of equation has a solution. And the main idea is that the solution will be encoded with the help of additional unary predicates. So per each variable from my system of equation, I will introduce a fresh predicate AU for each variable u from epsilon. And then the idea is that whenever I will have a structure that satisfies my formula, then a mapping that assigns to each variable the total number of elements satisfying the corresponding predicate should be a solution of our input system of equations. And we need to encode these three types of equations. So encoding the first type is easy. I can basically say that there is an element and there is precisely one element satisfying a u predicate. The second trick is to encode addition. And this is also quite easy once you remember the trick with equicardinality. So basically, we introduce a fresh predicate half. Then I say that precisely 50% of elements satisfy half. And then I say that the elements satisfying AU and AV sum AW are in different halves of a model. And once I have that, I can employ my trick with equicardinality statements to ensure that the total number of elements satisfying AU will be the same as the total number of elements satisfying AV plus AW. Of course, I need to ensure that the elements labeled with different variables are disjoint, because otherwise this trick wouldn't work. Right, so that's it. And then the last trick is how to encode multiplication. And we do that similarly as in the mentioned Ikai paper by Bader et al. And to encode multiplication, that U times V is equal to W, we proceed as follows. So first of all, we introduce a fresh unary predicate. We label half of the elements with half, and the other elements will be not labeled with half. And then what I would like to do is to introduce a fresh binary symbol mult, like multiplication, that will link every element from AU with some elements from AW. And I would like to ensure that every element from AU has precisely AV successors. Right? So every element from AU has exactly AV mult successors. And we can ensure that with this trick with equicardinality statements. And then I need to ensure that the inverse of mult relation is functional, and one can do that with a trick with functionality. It must be functional because otherwise some of the elements can glue together and we will not have a real multiplication. Okay, and by expressing all these properties, we can get the desired formula phi and conclude the undecidability of FO2 extended with percentage quantifiers. To wrap up, here is the short summary, and there are several open problems. So first of all, we'd like to know how to prove the exponential time upper bound for the finite satisfiability for GF2 plus local percentage counting. And as I told you, it's not that easy because you cannot really loop back elements in this construction of infinite tree-like structures. Then in our undecidability proofs, for example, for expressing functionality, we use the equality symbol. So can we prove undecidability of our logics without the use of equality symbol? And this is open for the moment. And the general question is there any decidable logic that is still decidable and can express arithmetical constraints? And I do not know the answer for this question. And whenever I touch something, it gets easily undecidable. And I do not have any candidates for this logic except some trivial logic like the one variable fragment. Okay, so that's all from my side, and I'm ready to answer your question.